So also, I'm really honored to be here, and I want to talk about a project and a subject that I think is enormously important, and it needs the help of everyone in the room and around the world. I want to talk about transforming what I know. I trained as a doctor and then went into biology. I've watched family members recently die from pancreatic cancer and other diseases. I know how Western medicine succeeds and fails, and we have to transform medicine. And so the talk is titled Transforming Medicine, Systems Medicine and Personalized Medicine. What I want to persuade you of is that we don't know what we're talking about yet. And systems biology, I think, is the transformative field that may help save lives, save money, reform our regulatory institutions, reform how we insure in medicine, reform the drug industry. It's going to be transformative, but we need to think. I want to get across, I wrote this on the airplane and I said, I want to explore 5 broad ideas, and you'll see I got to 4. I know I had a 5th in mind, but I don't remember what it was. That's a mistake too. The rest you can count, and they'll follow. So I want to talk about clinical fitness landscapes. So if you don't know about fitness landscapes, I have to tell you about them. I want to talk about nonlinear dynamical systems as models of cells, organs, and organ systems. Probably everybody in this room knows about it, but I want to go over it. I want to say the most important thing, we need new conceptual, mathematical, statistical, and experimental methods when multiple network causality, vast networks of interacting causes dominate areas of biology and medicine rather than single factor causes or single linear chains. We don't know how to do it. And I think that it leads towards the use of what's coming to be called big data in the United States, electronic data. And ultimately we want to get to personalized medicine, N-of-1 medicine, if we possibly can. So I'm not going to go over all the details in this below because I don't have time. I want to introduce you to, or name the idea of a clinical fitness landscape. So where does the idea of a fitness landscape come from? It really was stolen from physics, and Kim is here. Physicists know about them. They call them potential functions, and Kim worked on spin glasses, and spin glasses have very complex potential functions with lots of minima. Sewell Wright in 1932 said, turn it upside down, and going higher is good. The physicists stupidly want to go downhill in energy. Biologists want to go uphill in fitness, but it's the same idea. And a fitness landscape is characterized in lots and lots of ways. So I'll tell you that there are mathematical models of this NK model. I'm not going to go through it. I'll just tell you some of its main ideas. By now there's numbers of mathematical models of fitness landscapes that have found wide use in biology, in, believe it or not, in organizational theory and economics and other areas, in evolutionary biology and so on. I have to get across the following from this NK model, which, Kim, I stole from you guys. It's a spin glass model, okay? But I turned it upside down. I'll give you the feeling for it when I generated it years ago. You have N genes. Each gene comes in 2 versions or alleles called 0 or 1. So for all N genes, a given genotype with all the alleles is just 1, 0, 1, 1, 1, 1, 0, 1. It's an N-bit vector. There could be more than 2 alleles, so 2 is the minimum that's interesting, okay? Geneticists have talked for years about the idea that a gene makes a fitness contribution that depends upon the allele of that gene, but it may depend on what's called epistatically on the alleles of other genes. So it's called epistatic interactions. Epistatic interactions capture the idea of multiple causality, whether it's genes or biochemical networks or genetic regulatory networks or nonlinear dynamical systems in general. It's just a way of thinking about causal interactions among things that can vary here from 0 to 1. And in this NK model, everything else is done at random. So to give you the feeling for it, you pick each gene and you pick the K epistatic inputs to each gene at random. Then there's a way that I describe here to pick, so each gene now has its own allele and K inputs that have 0 and 1 values. So there's 2 to the K plus 1 combinations of their allele states. And what the model does is that it assigns a random decimal between 0 and 1 to each of those combinations of allele states for all 2 to the K plus 1 allele states for each of the n genes. And then you try to define the fitness of any n-bit vector, namely that allele combination for the n genes is the average fitness contribution of the n genes in those allele states. That's it. Now, I just want to tell you a few main things about fitness landscapes. If K is 0, each gene makes a fitness contribution which is independent of every other gene. More generally, the causal factors are utterly independent of one another. Okay? And that's a central idea. When that's true, you get a fitness landscape. I'm not going to define it more precisely, but think of the Alps or in Europe. Okay? In the United States, we think, of the Rockies. In the case that K is equal to 0, you get a Fujiyama-like landscape with a single peak. Okay? As the number of epistatic interactions or the multi-causality goes up, instead of having a single peak, you start having lots and lots and lots and lots and lots and lots and lots of peaks, ever more as the multi-causality goes up, as K goes up. Is that idea clear? Okay. There's lots of other features about landscapes, like the number of peaks, the lengths of walks to peaks, the number of directions uphill and how they dwindle as you climb towards peaks, the correlation lengths of these landscapes, whether they're NP hard, for example. These landscapes can be NK hard when everything is connected to everything and so on. An enormous amount is known about this NK family of landscapes. That's all I'm going to say about point 2 and features of the landscapes. Now I want to tell you quickly about a paper that came out in PLOS One. The authors are Margaret Epstein, Jeffrey Horbar, myself, and Jeff Bouzes. It's in PLOS One, November 2012. And we're trying to introduce the idea of climbing or searching on. The title is Searching Clinical Fitness Landscapes. It's a mathematical model. My moves are going to be to make mathematical models, then say we need to apply it to real clinical data for real clinical landscapes. How are we going to do it? And the big picture of where I'm going is we haven't the faintest idea how to do multi-causality well. What are we going to do and how are we going to get to personalized medicine? What I want to tell you first is something we found that's terribly important. We modified the NK model where we could tune whether or not each causal factor was independent of every other one, in effect K0, or tune whether or not causal factors interacted. You all know what random clinical trials are. They're the gold standard in the United States for the FDA, the Federal Drug Agency. Here's how a random clinical trial works. You take a whole bunch of patients and you give them some drug at some concentration. Then you take a control group and you don't give them the drug. You give them some placebo. And you ask, did the drug have an effect? Now what's important about this before I get started is that we all understand that we know exactly how to think about this. We all know. Gauss discovered the Gaussian curve, the bell-shaped curve, from which we know the mean, from which we know via a t-test whether the mean of the experimental group is statistically different than the mean of the control group. We all know that. That's standard statistics. What I'm going to tell you is that we don't have any idea how to think about a multi-causal system and what these statistical distributions of effects look like. And that's part of what we have to discover. That's part of what we don't know how to do. Meanwhile, what we did in this model is we imagined that there were 100 hospitals and there was 100 possible treatment modalities or causal factors, binary, just low and high. And we asked, can we learn good combinations of 100 different treatment factors? And we tried random clinical trials for K0, the Fujiyama landscape, and then for causal interactions where the landscapes multi-peaked. I knew what was going to happen. This is the only thing I predicted. If K is 0, so the landscape's a Fujiyama landscape, and all causal factors are independent, random clinical trials works beautifully. As soon as multi-causality comes in and there are multiple peaks, it fails. Ever more as multi-causality increases. And the reason is that you can't get statistically significant results for your t-test. It just fails. Pause. In the United States, and some analog must be true in Europe, passing random clinical trials, phase 3, is the sine qua non for getting FDA approval for a drug or a procedure in medicine, but not surgery and not in veterinary medicine. So we already know that this procedure is going to fail. Okay, so I'm going to come back to that in a second. My friends invented something called team learning, which is borrowed from quality improvement groups. The basic idea is 10 hospitals, 10 teams of 10 hospitals. Each team has the property that they treat a very small number of patients, 40. It's nearly anecdotal. And on very weak statistical grounds, they simply keep picking the best one out of the 10 hospitals and retesting and trying to learn. Team learning, invented by my colleagues, not me, radically outperforms random clinical trials, just overwhelmingly as K increases. Therefore, there's a better way of learning when multi-causality is present than being frozen into the gold standard of random clinical trials.